Everyone, any question from yesterday lectures or assignment they want to talk about? Sorry? Oh yeah, I haven't put it yesterday lecture notes. Yeah. This lecture note is a bit delayed. I got like 3 lectures and 2. So I didn't prepare on time. So as I'm still writing it, I will put it out hopefully later or tomorrow. Yeah. It's this Thursday class. Is I will put up the notice again in the exam content. Check. Okay. If not, let's resume to yesterday lemma. So let's recall the definition we had first. So what are the definitions we defined yesterday? So we define a separation of a topology, a topological space. I mean, so what's the separation of a topological space? Is a pair. Is a pair of what? Is a pair of open and then non-empty. Okay, we don't want to put empty set like that. And disjoint disjoint set U and V such that X is equal to the union of U and or disjoint union. And if S has no such separation, then we will say that X is called connected. I will say that S is connected. It's called a connected space. Or it's connected. Okay. And what else? How about a subset of a topological space to be connected? So a subset A of X is connected if it is itself a connected topological space when given the subspace topology. Okay, so when you read this definition, right, you see when I write A, I just start from a subset. I didn't say a subspace. I didn't say a subspace A. I said a subset A. X is connected. Okay, how is it connected? Okay, how is a subset connected? If it is a connected topological space. But I didn't tell you what's the topology on subset yet. I just said subset. I didn't say subspace. So how is it a topological space? When it is considered as a subspace topology. Okay, on that subset. Does it make sense? Okay. So when you talk about subset of a topological space to be connected, usually we just consider the subspace topology. Again, not any random topology you put on the space. Okay. Okay, and then lastly, we give this criteria of checking whether a subspace is connected. Instead of looking for these non-empty, empty, disjoint, open set, instead, if um, if you are if you are separation of a subspace, okay, really, the pair of subset, sorry, the pair of set that make out your subspace, we can characterize using the limit point. Okay, so what do I mean by that? So if Y is a subspace of X, a separation of Y is a pair of disjoint non-empty set A and B such that the union is Y. And neither of which contains a limit point of the other. And then we can prove that the space Y, the space Y is connected if and only if there's no separation of Y. Okay. So what's this lemma asking? Just now I defined already how subspace to be connected. So actually we need to show the equivalence between the two definitions. Okay. Right. Just now I already described how a subset to be connected. And then here we give another criteria for the separation for Y. Okay, if there's one. So we are trying to show equivalence between these two. You can take it as a definition here, right? Background just come in. No, it's okay. I was trying to kill you because yesterday you mentioned about if I can write a space into two open set, right? Yeah. What's the distance notion you are trying to say yesterday? Can you repeat again? And since it's disjoint, so the distance must be greater than 0, not equal. It's just like that. Okay. So here saying that if you are a separation of Y, okay, and this two pair union to your whole subspace, but neither of them contain a limit point of each other. So you cannot be infinitely close to the other set. Okay. So I think it's a bit similar to what back home said. There's a distance between them. Okay, cannot be infinitely close to it. Okay, but here we didn't use idea of distance already. Here we use limit point. But how we define limit points? Remember how we define limit point in topology? Like open neighborhood. Okay, we use neighbor open to do it. Not the delta ball, not the D ball again. Okay, we use the neighborhood. Okay. All right. So how to prove this? Kind of straightforward. So let's do it. So let's prove which direction first. Maybe prove this direction. Okay. So prove that if there's no separation of Y, which is given by the limit point condition, then it is not. Then it is connected. Okay. So to prove this, we will use contra positive. So suppose first Y is not connected. So what does it mean by this subset Y is not connected? Then you can find disjoint, open, non-empty. Okay, the point is here, when we look at the disconnectedness in Y, this open subset, right, is really open in Y actually. Okay, it's not in the largest space. Okay, but in Y as a subspace topology. Okay, it's open in Y such that Y equals to U union V. Okay. From here, what can you see? You can see that you can find one set which is closed and open at the same time. Maybe not just one, both of them. Okay, let's look at one first. As U equals to Y minus V, U is both open and closed. Right? As a complement of open set, you are closed by definition. The complement of open set is closed. A set is closed if its complement is open. So since U is closed in Y, okay. I think last time we proved that this U is really equals to U bar intercept Y. What is U bar here? This is the closure of U. But where do you take the closure? This closure is taken inside X. Okay. Remember last time we don't denote the closure inside Y because there's some criteria for a subset for a set to be closed inside a subset. Right? So a set inside a subset, I mean, there's a criteria to talk about whether a closed set in the subspace is closed implies it is closed in the original space. Okay, this is only when the subspace itself is closed. Okay, closed set of a closed subspace is closed in the original space. Okay, this is what we proved last time. So when we take closure of a set, usually we take closure in the original set. Okay, so since U is closed, we can write U. Since U is closed in Y, we can write U as a closure of U in X intercept with 1. Okay, subspace topology here. Does it make sense? Okay, no. U is closed in Y meaning what? It has everything, every limit point in Y. Okay. In particular, you can gain this limit point from the closure of U in X. Yeah, right. U in X. Okay. Any question on this one? Okay. So since U intercept V is empty, okay, this is by definition, we can look at what is U bar intercept V. What is U bar intercept V here? Yeah, why? Because U is U bar is equal to U. U is equal. Oh, that one happened in the U equals to U bar is when in the original space in the X. But here we talk about U closed in Y, so U is equal to U bar intercept Y. Okay, but what did you know here? This intersection here, let me see. So this intersection here really equals to U bar intercept Y intercept V. Is it true? True, right? Because V is in Y. So if you want to lie in V, you must be lying in Y. Okay, and then what do we know? We know that U bar intercept Y is U, which you get U intercept V, and then this one is by definition empty. So V does not contain any point in U, in particular the limit point of U, right? Because we proved that the closure of U is all the point of U and the limit point of U. Yes. So there's no intersection between them. V don't contain point in U, also don't contain limit point of U. Okay, so by similar argument, we will also find that U does not contain the limit point of V. Okay, same argument. It's a symmetry argument. Okay. Okay, so I'm not sure when you read proof, right? What are you thinking about the proof? Are you just focusing on the result or what? Okay. For me, when you look at the proof, right, we want to know how to go from assumption to the goal. Okay, so this proof will discuss, okay, how you go from the assumption to the goal. This part is important. Okay. I'm not sure how much I said this makes sense to you, but please think about it, because this will change your way of looking proof. You will make proof become your second nature. You know, proof is just not like some working, but it is telling why something is true. Okay? This will change your view to proof, and then how you listen to people when they prove something. Okay. Okay. So any question on this part here? Is everyone okay with this direction? Okay. So next, let's do the other direction. Let's do the other direction. Which direction we want? So suppose that Y is connected, okay, and then there's no separation. Suppose that Y is connected, then there's no separation. Is it? Yeah. This direction. All right. So how are we going to prove this? Again, we use contrapositive form. Okay. So in this case, we'll suppose that U and V are disjoint non-empty set. Okay, there's no open condition now, right? We give a new criteria for separation of Y, remember? So we just require them to be disjoint non-empty such that Y equals to U union V. Moreover what? None of them contain the limit point of each other. Okay. So you can think of it like, in any set, there's no point arbitrarily close to a point in the other set. Okay. Or like Pehom say, no arbitrarily close, then there's this some. If it is a metric, then you can put a delta or epsilon there. There's an epsilon gap there. If you can put distance to measure it. Okay. Otherwise, you just understand it as a neighborhood. There's not infinitely many neighborhoods. Okay. Right. So then what happened here? Then U bar intersect V should be empty, and U intersect U bar should be also empty here. Okay, because U and V already empty, you put in limit point still empty because they don't contain limit point of each other. Okay. Sense? And what? So the claim here is U bar intersect Y is just U. Okay. The claim here is we can retain this condition here. If we retain this condition here, what does it mean? just now we have used this fact, right? If U equals to U bar intercept Y, then U is close. If U is close, V is if U is close, wait, if U is close, V is what? V is open. Okay. And because we got similar property here, right? You can also prove that V bar intercept Y equals to V. So in this case here, V is closed, U is open. So both of these are both closed, both open. Okay, so you have written Y in terms of disjoint non-empty set of open subset. Okay, then we are done. So how to prove this claim here? This claim here, you can see from easy set theory manipulation. So for example, U bar intercept Y equals to what? Equals to U bar intercept U union V, because this is by assumption. Okay, and then we can distribute it. So if we distribute it, we get U bar intercept U union U bar intercept V. Okay, but U bar intercept U is just U, and then union with what is U bar intercept V? Is empty. So you just get U. Okay, so similarly, we get V bar intercept Y equals to V. Okay, so what does this mean here? Thus, by definition or by some proposition, U and V are closed in Y. This is what I think I remember. This is what we proved last time. Yeah, we proved last time. The closure of U in Y is equal to the closure in X intercept with Y. Yeah, this is what we have proved last time. Okay, you should check it out. This is from last time you learned. Okay, and as what? As V equals to Y, take away U, and U equals to Y, take away V, they are open in Y. Excellent. Okay, make sense? Okay or not? U and V are close, so you take their complement, they are open. Okay. Y take away U is just V, so V is open. Y take away V is just U, so U is open. The next question, yeah.
Say U is closed, and then I can
That's the beginning part.
before you write.
Oh yeah, so right. So now we deduce U and V are close, right? Okay. So my claim is I can deduce from U is closed, I can deduce V is open. Does it make sense? Why? Because V is the complement of U. Yeah. Okay. And from V close, I can deduce U is open. Why? Because U is the complement of V. V is a constant. Okay, good. Yeah. So these two sets are open, and then by definition, they are by assumption, they are disjoint, they are non-empty. So this is a disjoint, non-empty, open. So this one is a separation. Yeah, it's not connected. Okay, it's not connected. It's a separation for Y. Okay, so far so good. Okay, we will see some example pertaining to this theorem and also definition of connected. Yesterday we didn't really give any definition, right? I mean examples. Okay, so today we will look at a few. So let's look at a few. Let's look at the 2-point set here, AB. Okay, with indiscrete topology. Do you still remember what's the indiscrete topology again? 不小心. Why is it 不小心? Indiscrete. What's the indiscrete topology? Discrete is what? Sorry? Every subset, right? So indiscrete, not every subset, but you consider what subset? Empty and the whole space. Okay, empty or the whole space. So these are the two open set you have here. So can you write this set into the union of proper empty, two proper non-empty open set or not? Cannot, right? Only you get everything or you nothing. Nothing cannot be the whole space, right? So you only get the whole space. So there's nothing for you to separate it. Okay, so this is not connected because there's no non-empty proper open and close. This is one of the TFAE we proved yesterday, right? Okay, the only what did I say? Not connected. Oh, this is connected. Because one of the TFAE we proved yesterday, the space is connected if the only open and closed set is the whole space or the empty space. Okay, so this is connected. You cannot separate it, okay, by two proper subset. How about this one? This subspace topology here. -1 to 0, union 0 to 1. Is this connected or not? Or disconnected? Why? What's the U and V you can take? Yeah, so you simply consider the interval U equals to half closed at -1 and open at 1, and B to be open at 0, closed at 1. Then Y equals to U union V. Okay. This two set is open in the subspace topology, but it's not open in the whole space. Okay, it's open in the subspace topology, but it's okay, right? Because we are consider it connected in the subspace topology sense. Okay, and what did you observe here? This two open set here doesn't contain limit point of each other. What's the limit point of the half closed interval or half open interval -1 to 0? What are the limit points here? Huh? Not just 0, eh? Yeah, so it is the limit points of U should be everything from -1 to 0. Similarly for V, okay, you have everything from 0 up to 1. If you're not sure why this is true, I suggest you go and prove it. Okay, go and use the definition of limit point to prove this. Okay. Okay. What else? Let's look at Q. How about Q? Rational number. Connected or disconnected? Can you find a separation for it or not? How? Sure. So you could write this one as negative infinity to square root 2 union union with square root 2 negative infinity. Is this enough or not? So you need to consider the subspace, right? You need to consider the subspace. So like this. Okay, so this is a separation for your rational number. Yeah, or not just square root 2, like just find any irrational. What do you mean?
He already in the two numbers. No more correction, nothing. Yeah.
So this interval here is defined to be, so A, B is defined to be everything in R such that X is less than B, greater than A. So we don't want irrational. Okay, so this open interval here is open in R. Okay, so if you intersect with the subspace, you will get something open in the subspace. Okay, so you are union of two open things inside the subspace, and then what? And then they are destroyed, and then they are non-empty. Okay. So here we will say that Q. We haven't concluded the previous one. No. Let me write down. So Y. So here Y is not connected. Then here Q is also not connected. Q's are not connected. Okay, but surprising fact here, Q is not connected but it's still dense. Very weird phenomenon. Real line is very weird. Yeah, that's why, yeah, real line is very weird. Okay. So, how about this? How about this two set here? So let's consider some subset in R2, which defined by this algebraic property here. So let me write it down and then we will draw it out. In meanwhile, you can try and think what is this two things here. How to graph this two graph. In the first set, what you get is really the x-axis. Okay. X-axis here. Is it hard to see? About okay. Deeper. This. Okay, so this is the first one. About let's call it a name. Let's call this x1. Let's call this x2. So your x1. How about x2? X is everything positive, and then y is 1 over x. So this graph is the other part of the 1 over x graph. This one. So this is x2. So this is connected or disconnected? Huh? Disconnected. Why? Can you convince people why? Huh? Yeah, so you can use the argument that these two sets don't have limit point of each other. Okay, you can use the argument that these 2 points don't have limit set of each other. So when you ask about this, then you need to go and find what's the limit set of this x-axis here. Okay, what's the limit point of x2 here? If I'm not wrong, then I think they are both close already. Yeah. You can try and prove. Or try and prove. x1 bar equals to x1, x2 bar equals to x2. Okay. Okay, next one, maybe last one before we go to more property. So let's take this one. How about the lower limit topology? Is it is it connected or not connected? What's the lower limit topology? It is built up by half open interval, right? Where you close at the left endpoint, AB, and then close at A, open at B. Connected or not? Huh? Connected. Why? The only open and closed subset of RL is RL and empty. In fact, it is not connected. Exactly, they are proper subset which is closed and open. So what is the proper subset that's closed and open? You can simply just look at the half open, half closed at 0, half open at 1. This guy is non-empty, first of all. And it is proper already, very easy to see. But why is it closed and open? Open is easy because this is one of the basis elements. But why is it closed? How to show a set is closed? Definition. Yes, complement is open. What's this complement? What's the complement of this guy? Negative infinity to 0 and then 1 to infinity. So this is two open set in the lower topology. Union of two open set in lower topology. So you see another thing you see is if I found this non-empty prop, really your RL is just this complement plus the original set. So you produce a separation. Okay. So if you can found this proper close and open at the same time, then the complement and that set will form the separation. Okay, this is actually what we proved in the TF&E theorem. And then you see it in this example. Okay. Okay. Any question? Or question? Yes. Previous. Which one? Second example. This example. Okay.
0 is the limit point.
0 is the limit point for both U and V. Yes, that's right. They don't contain, right? Because I throw away U. I'll throw away that point. Yeah. I try in both U and V, you cannot find 0. 0 is just their limit point. I must be in. They cannot contain limit point of V. They don't contain here. Because I throw away 0 in U, I throw away 0 in V. That's the point of this question. Yeah, I take away the limit point from both. I mean, if I wrote in this sense, yeah, if I change this question, if I change this question to this, connected or not? This space. This space is really -1 to 1, right? And you need to prove what you need to prove. Later we'll prove it. Later we'll prove that any interval in real is connected. Okay, later we'll prove it. Because you want to prove it connected, you need to show there's no separation. If you want to prove existence, then you just need to find one. Okay, but to show there's no, then a bit troubles. Okay, no? Okay, so if I include limit point to one of them, then I get connected space. Okay, later we'll prove it. So this one later we prove it. Later we will. Later we will prove it. Okay. Then got still how many more time? Oh, actually we will prove it now. Okay, let's prove it now. Okay, let's prove it now. So next thing in this agenda is exactly this theorem here. So A is connected in R with the Euclidean topology if and only if A is an interval. Okay, so interval here quite wide. The interval here would means something finite. Okay, close, open, anything we all included. So something like this. Also something like open first and then close it. And you will see that some of the book will say rays one side become infinity. So maybe negative infinity to B, negative infinity to B, open or A to infinity, or including A to infinity, or even we consider the whole real line. Okay, these are all intervals. Okay, you see that this theorem, do you feel that this theorem is a bit the same flavor of what you have done in the assignment? Open, if you can write as a union countable union of interval. Okay, so this kind of questions says what? Actually, at first, you don't know how to think about the connected space in the topological space. But you use the property of connectedness to deduce that A must be a interval. Okay, you get what I mean? You don't start by thinking first, oh, my connectedness are these interval, and then you prove that these are this one. Okay, you will see this phenomenon in the proof later. Okay, you'll see the phenomenon in the proof later. So okay, so let's do it. Let's go this direction. So if it's connected, then it must be an interval. Surprisingly, this part is easier. Okay. So we will use a contrapositive. Okay, so if A is not an interval, meaning what? Meaning there exists A and C, 2 points in A, and a point not in A, such that what? Such that this point lies in between A and C. True? Is it true? True or not? If you are not interval, then there's 2 points inside your set such that there's 1 point in the middle is not in the set. Negation of definition of interval. Negation. Okay. So what? So I would use this to build my separation now. So this is really similar to how we show that rational is not connected. So what I'm going to do is I just simply take U to be negative infinity all the way up to B, intercept my set A, subspace topology, and V equals to B, comma, infinity up to intercept with. Okay, then these two will provide the separation for A. Then this will provide a separation. So A is not connected. Okay. So another piece of advice. Every time I finish a proof, I want to give you a piece of advice. So when you follow my proof, right, please don't just follow. What do I mean by please don't just follow? You need to know what I want to do first. Okay, and then I will tell you what to do. You cannot come here, you don't know what you do, what you want to do, and then you follow what I ask you to do. You get what I mean? This is living in the core whether you can understand what I say or whether you can question what I say or not. Because you need to have a clear goal where you are going or where I am going. Then this is where we have what's say suddenly think of the Malay word. Pertembungan. So it's like Chinese is like 交锋. So it's like English is what? Clash of ideas. Okay, clash of ideas. So only here there's a clash of ideas. Otherwise, not only you cannot follow my ideas, moreover you will lose. Okay. So if you don't want to lose, make sure you know what we want to do first, and then you can follow what I'm talking about. Okay. So keep going. Sorry, a bit detour. Okay. So next, we prove the other direction. Suppose it is an interval. So meaning one of these things, okay, one of these things, any of these things. Suppose it is one and any interval, okay. And then we want to show that it is connected. Meaning what? There's no separation, okay. So there's no separation. So what? So we use contradiction. Suppose there's one, and then see we can make contradiction on. So suppose A is an interval. Okay, so to see that A is connected, suppose on the contrary that we found a separation for A. So let's say we found a separation for A. Let's call it UV again. Because they are non-empty, right? Okay, they are non-empty. So I can pick one element from U, little u from U, and little v from V. Because they are non-empty. Disjoint open. So without loss of generality here, we will assume one is greater than the other. Okay, so let's assume U less than V here. Yeah, because this is the order axiom in real number, we can compare any number. And then if V greater than U, what happened then? What to do? I simply swap the two set. The other I call U, the other we call V. I just swap the naming, it's fine. But in the end, we will have something less than the other. So what do I do here? So I consider this set here. This set of Y such that U comma Y bracket is in U. Okay. So I want to see how far behind U is in the set U. Okay. How far behind the little U is in the set U. Okay. I want to see how large this interval can grow. Okay, so that I can lie inside U. So can you predict what I'm trying to do here? What the set of real numbers? What do we always do with set of real numbers? So okay, let's give more condition to this set here. So this set here is non-empty, right? Why is it non-empty? Why is it non-empty? Yes, U is in there because U is with the one we pick from U, capital U. So since the little u is in there, and moreover, this set is bounded above. Bounded above by what? Bounded above by what? V, right? This set is bounded above by V. Okay. So it is a non-empty bounded above set. Meaning what? By completeness axiom. Completeness axiom. Sup X as this. Let's call it a B. Okay. Sup X as this. Okay. So we want to ask where this sup X lies. Where can this sup X lies? Okay, where can this sup X lies? Where can this sup X lies? Now what happened here? Let's see what happened. Now, you can see that this B, right, should be less than equal to V or greater or equal to U. Right now? Okay, because V is the upper bound of the set, but B is the least upper bound. So it must be less than or equal to any upper bound. Okay. And A is an interval that contain what? Containing U and V. Okay, so what? So actually this B, right, have to live in A. Okay, just that I don't know it live in U or V. Okay. Live in A, but I don't know whether it's in U or in V. Okay. So what's next? Contradiction, huh? Because these two are disjoint, right? So let's suppose live in one first. Okay, so suppose first if B live in U, what happened? U is what? Open. Open. So means what? There exists a epsilon such that what? B minus epsilon comma B plus epsilon. This open interval here is living inside U because U is open. For every point inside an open set, you can find a open neighborhood. Okay, and then can draw contradiction or not? Then what? Sorry, B what? Sorry, then how to build this larger upper bound? Who is the larger upper bound here? What? Yes, so you can consider this interval here, U all the way up to B plus epsilon over 2. Okay, this interval should live in U. Okay, so meaning what? So B plus epsilon over 2 is in X. B plus epsilon is something greater than B. So this one contradicting B is equals to sub X. Okay, so it cannot live in U already. In this case, still got one chance, man. Maybe this in B then. I don't know. Hmm? I think what you're trying to say. U is open in.
So the
Mhm. Oh, wait, let me think carefully. What you're trying to say. Let me think. Let me think carefully. So you say that this U and V is open in A. Yes, yes, yes. Okay, yes, yes, yes. Let me think. But is it equivalent here or not? Let's say Let me think. Wait. Which direction we have? We already know that this is right. So correct. So you are right. So U is open in A, but if you take this intercept with A, I think the claim is you can find an epsilon such that it is just equal to some. It is just equal to some. Okay. So if you want to take this epsilon, this guy intercept with A, right? Okay. Like this. What I want to say is, if you take an open set of open set, okay. Let me think how to phrase it. What I want to claim is, even if you intercept with A, you still get open. You still can find an open interval that looks like that, because A is an interval. Make sense? Does it make sense? But what? What's the problem? If you think this is too big, then you shrink it, no? You shrink until you live inside A. So what's the problem?
If I drop it off because A is interval, so that's one. In the A. And because the A not in the U, so it's in the B. A is like B minus S1 plus B constant.
A is lie inside. You mean A lie inside? That's what I said. You can find a smaller one. You can find a smaller one such that the bend is true. You get what I mean? Because we assume A is an interval already. If you like, okay, if you like, let me think. How should I put this? I mean, I can shrink this interval to prevent your case, right? Do I need to shrink to prevent your case? Because I already split my A into two disjoint union. So I can't be open. Oh, maybe you think that it's open until intersect with non-intersection with V, right? Your problem. You scared there's a non-trivial intersection with V, right? But this U and V intersection is empty, right? We will assume that. Yeah, we assume that U and V is empty. So will you get the problem? U is open in A, true. It's open in A. This is true, and then sure. Somehow I get your problem, but I cannot phrase it precisely now. Can you write to me? Write to me. I try and phrase it precisely because I suddenly cannot phrase it precisely now, so I cannot answer precisely. I somehow get your question, but I cannot phrase it precisely. Yeah, because it's like open set. Because you remember this open set will do something weird. I mean, not weird, but yeah, it just get that this open set will have non-empty intersection with it. Well, I'm trying to argue that this can't be happening, but yeah, you can write to me. What's your concern? Write to me. What's your concern? Okay. But what I want to claim is you can find some interval, okay, around B that live inside you. Okay. There's no, I think there's no gap here, right? There's no gap here. Other disjoint like B, right? So because usually open semi-index, so that I can keep a record. Okay. So we proved that it cannot lies in U. How about in V? Can it lies in V or not? Can it lies in V or not? If it lies in V, right, V is also open. So you can find this similar open interval here. But what's next? What's next? But what's next?
B minus F1.
Wait. So are you trying to answer this or you still keep this one? Okay. So since B minus epsilon over 2 is in V, meaning what? In V, because you shorten.
The B is not of S.
Okay then.
So the B minus epsilon over the U to B minus epsilon over 2 is in U. Close.
Okay, let me finish and then we can discuss what you say. Let me finish, I can discuss what you say. Okay, so B minus epsilon over 2 is in V. Anyone disagree? No, right? Because this is a bit further from B minus epsilon already, right? And then what we have? And actually, you can consider the whole thing from U to B minus epsilon. This thing cannot lies in U anymore because B minus epsilon over 2 is in V already. Okay, but this means what? What does this mean? This would imply that B minus epsilon over 2 is an upper bound of X. So you found something smaller, which is an upper bound. So this one contradict B is a supremum of X. Yeah. Why can we take the infimum of V? This is not the thing we are discussing, right? What's wrong with that? Why? I mean, you want to look at. Then in that case, you need to prove that this soup is equal that inf, so you need to do different construction. No, I didn't say cannot. Then you need to create that. You need to prove that soup of that is the inf of the other thing. Then you can use your inf argument. I didn't use that, so it's not involving those things. I didn't claim that. You should work it out. You should work it out. Okay, because you think of that, you should work it out, and then you can really see that they are the same. I mean, similar. You should work it out. Can or not? Okay. Okay, so the problem here is just we want to contradict that the B is not a supreme. That's all. Okay, any more questions? Any more question? Yeah. If you can work out the infimum thing, you can send to me. Yeah. Then we can see this problem with different view. Yeah, it's the same view actually, but from a different direction. Any more question about this? So we prove that if you are a connected subspace in R, then you are an interval. You are an interval. Hey, actually, I mean, before we take a break, so just end this part of story. So it is the yesterday we have seen it in the generality But today we have proved that intervals are connected, so we can use what we have proved yesterday, continuous image of a connected set is connected. So this is the intermediate value theorems. So the corollary of this theorem is intermediate value. Okay. Together with the continuous image of a connected set is connected. All right. All right. So let's take a break. Let's take a break until 12:17. Go up. Go away. Just here. Yeah. I ask you guys about course taking in this union. If let's say you take a course in the middle, can you change course or not? You like drop and back? Cannot. Not time limit. Or after 3 weeks, cannot. Okay. And then is there a policy that if you drop course in the middle of the course before ending, maybe before exam, then there's a refund, partial refund of the thing. No, automatic. Completely not. Because in our university, there's a hardware you can drop. Maybe you get some refund. Possible one.
Study until the half semester, then drop this course.
Can because you think that you cannot handle, like for example, 4 courses in 1 semester. So you become underlocked. Then you need to take it. Because underlocked, you cannot handle all the courses. Yeah. In Australia, they are quite free, like. Yeah. Yeah. I was wondering also. I asked you. So. Huh? Holidays means what? Oh, right. I think another problem about this holiday is Malaysia is really too much holiday. Because Australia also got holiday, but not many. Just few Fridays only. But Malaysia suddenly this birthday, that one festival. Festival got few types of races, one religious one. They have summer breaks. Yes, that's true. That's true.
I think summer break is around
2 weeks.
all 2 weeks.
We got 2 weeks. 2 weeks. Yeah. So they are only cover 11 to 12 weeks of material. So let's say we want to do it here, then cut it short to 13 weeks or maybe like that. But if you okay, if like maybe your argument is like, since your holiday is dispersed, right, treat them as a summer holiday, no? But the problem is what? The problem is the course design here is for full 15 weeks. It's not like for 13 weeks, not like that. So it's hard to do that. But for Australia, it's like they plan it for 12 weeks. So the middle holiday is definitely a holiday. Nothing to learn there. So this is actually related to how the course is designed.
Summer break you are assumed to be break, but during those like the semester when
We call a lecture break. We call lecture break. So there's nothing to learn there. So I mean, this is I think they need to do some reform of this higher education. Higher education.
in Australia.
We have no. We split hourly. We split, for example, every maths course we have like 4 hours of lecture, like 1 hour, 1 hour each. 1 hour then by like you go other class. So like 4 hours of lecture, 1 hour of tutor. But here they like to put it as a block. 3 plus 2, 2 plus 2. One thing is easier for scheduling. The other thing is they don't know how people study. It's like going tuition. I used to go tuition. That's why. I purposely make it public. So I mean, how to say? It's like tuition. I remember like last time I got English tuition also like 3 hours. Yeah. I don't think it's good for learning curve. Agree, huh? I think we need to reform. I don't know. Seems like the government, those higher educational one, is like don't know how to study one. So that's why they make this kind of stupid policy. True. True.
Actually, you think of like middle school, you go to school like that, you think you can learn much. I don't think so. It's very hard to learn actually.
No.
Like you can see that at least like 60 or 70% of students cannot being.
Then what you talk about secondary school, huh? That one is for education, huh?
Yeah.
Ours is like higher education, but both are problem, huh?
Yeah.
Anyway, both got problem. Yeah. There's a study. There's a study about secondary students or primary students. They are learning like only 80% of they should learn.
80%.
Oh.
80% I don't trust. Actually,
That one is the upper bound. That's the upper bound. Upper bound. Yeah. So I mean, I don't know. They don't like to study, so they don't know how to study. So what's important here? Politics. So you want to reform education, you can go politics. Why you become one of them?
No.
You don't become one of them.
It's not that easy to become the outstanding person.
Yes.
Inside the government, because if
Sure.
you want to change them
Sure.
by their power, their things you cannot change it much things. I also think about this thing.
That's why this is the fall of the first PH government. Because they want to do what they want, but even the KSU, the University of Sahara, the next one of them, they don't want to do. You know what they say? the day when they want to like the government change, like they feel that their government is not stable, actually those government servants don't listen to them already. They already feel the changing. So what does this mean? So this is what they call the deep state. Because the real executive power is held by these government servants, you know. It's like I'm a teacher, like you're a student. If I set 10 assignments, if you don't do, then that's mean don't do all. No one will do it one. Because execution on you, not on me. You know, if I set 10 question, 10 assignment, you don't do that, there's no 10 assignment. It's not I say what, you do what one. No, you can choose to not do one. And then they choose to not do, then the government fall. Yeah. You don't simply think this is easy, you know. You know. So I mean I'm grateful. So at least got a group of people like want to follow this kind of rules. If no one want to follow, then no point in saying it already. Actually, this class got a small portion of people trying to break the rule. I think it's even worse than the class that I taught before. I thought the class I taught before is quite worse already. But now it's not that they want to break the rule because they wanted to, because I think more to that, they don't have the ability to learn already. This is what I'm really worried about the students in this maths department. They don't have the ability to learn. This is a very bad thing. Not competitive graduates. Not competitive graduates. Okay, so this is the thing I'm very worried about. Okay, so let's start. Sure. Next, what should we discuss about? I think this example here try to answer what our question yesterday. Can we always find a homeomorphism between closed and non-closed set? Okay, today we will look at one example of it. Okay, one example. We will say that the closed interval 0 to 1 is not homeomorphic to the open interval from 0 to 1. And it's not. Sorry, it's not. And it's not homeomorphic. Let's see if we can draw some contradiction. Suppose it is homeomorphic. Okay. Let's see, can we draw some contradiction? Suppose there is homeomorphism F between 0, 1 and close interval 0, 1 and open interval 0. Okay, what can we do here? We can look at the image of F1. Okay, so image of F1 simply must lie inside the codomain. Must be some point in the middle of 0 and 1. But let's say let's remove 1 from the closed interval 0, 1. What happened? What do we get? What do we obtain? Sorry? What 0, 1? A lot of 0, 1 here. So I need to be a bit precise. Yes, close at 0 and open at 1. Open or not, this guy? Sorry, this guy not open, yes. Connected or not? Connected, right? Just now we proved any interval it is connected. So we get this guy connected. Then let's remove 1 from the open interval 0 and 1. What happened? Then we get 0 up to F1 union with F1 up to 1. Become not connected. What is it trying to say here? Any contradiction? I'm doing extra operation here. I think we haven't get a contradiction yet, but we need this claim to get contradiction. So if H is a homeomorphism, then H acting on X removing 1 point and to Y removing 1 point is still a homeomorphism. Then here we will get contradiction. Why? Because continuous image of a connected set should be connected. Okay, so you need to prove this claim first. Okay, no? Okay. I think this claim should be not hard to prove, so, but you need to try and show continuity bijection. Bijection should be easy, right? Bijection should be easy, but you need to check continuity. Okay. That's why. Yeah, you can just use it, but I mean to prove this claim. I was trying to say you need to prove this claim. Yeah, use it is immediate, but you need to prove this claim. Okay, to prove this claim, what you need to do? You need to show that this H here is bijection on the new domain, codomain. This is quite immediate. How about continuous? Okay, so you need to consider, I mean, really you just need to consider the open set. Where? Yeah, open set. Open set. Yeah, you need to consider all the open set in the codomain. But the open set, the codomain should be some open set in the original domain. So the problem is whether the inverse of this guy is still open. So does it avoid A? If it avoid A, then it's the original open set. Okay, but you should try and write it out. Yeah. Does it make sense? Okay. No? Okay. So with this claim, then you can produce the contradiction, because even if you remove 1 point from the domain and codomain, it is still a homeomorphism, and continuous image of a connected space should be connected again, but you split it out. Okay. Okay. So to this end, we will define some interesting terminology. So suppose S is connected topological space, and an element A in S is a cut point. Okay, maybe it will remind you some of the graph terminology, graph theory. But an element A in X is a cut point if X minus A is not connected. So meaning you are connected space, but if you remove this point, your space become not connected. So it's like a knife flow, right? It's a knife, like a knife. You cut it like that spot, then it's separated. So we call it a cut point. Okay. Otherwise, if you cut it, your space is still connected, then we'll call X is non-cut point. Okay, that's all. And nothing special here. So, and then, so we got non-cut point, cut point, and then a subset A in X such that X minus A is not connected. Then we'll call the whole set to be a cut set. Okay, so I collect all the cut point together, become a cut set. Okay, so this I want to, can I talk about it now? Let me see. Let me see, should I talk about it now? Yeah, maybe I talk about it now. So, right, so let's talk about it now. So, for example, in calculus 2, right, you have this kind of example. What example is that? So it's like a rose graph. How to describe this rose graph? Yes, using the polar curves. Using the polar curves. Can you identify any cut points here? You cut it such that this whole thing is not connected. I mean, let me separate into two cases. These two are not connected, obviously. So let's break it into two. So can you identify cut points in these two cases? You just take away the middle point here, the origin. I mean, depend on how you place this guy. So if I just draw like this, it's quite topology. But if I want to talk about the real curve, then maybe I need to write down the algebraic equation. So for example, this one is what? The example, I can't remember. But I think you think about this on your project, right? Did you take this? Forget forget also. Huh? Cos or sine? Use cos or use sine? Sine? You sure? Sine. Okay, sine of 2 theta. Okay, maybe you can check it. This one? Sine 4 theta? Okay, I'm not sure. I'll check it. I'll also go back and check. Check of course. Cos. I don't know, but just check it. Yeah. So these are the suggested answer. So what I wanted to say is once I fix this algebraic equation for equal to r, then they are treated as a geometry. But previously we are just some floating object in the space. Okay. So if we fix the geometry, then we will know exactly the position of that cut. We can exactly know the position of that, which is the origin. Because you can imagine I can simply shift them anywhere in the space. But the cut point is the point that is common to. Later we will say that these are all the connected components. Okay, later we will introduce this word. But we will see again this example. So for now, right, to prove that this is the cut point, right, you really need to prove that the whole space is connected, and then after you taking this this point, then it becomes not connected. You need to prove that. Okay, prove that after you taking this cut point away, what is left is not connected. So to prove that it's not connected, you need to find what? What do you need to find to show something not connected? What do you need to find? Separation. Okay, what's the separation? The separation is exactly this part here and this part here without the point. You need to show it. Okay, show that it is open. All right. What's next? Okay, let's go on. Lemma. If the set C and D form a separation X, and if Y is a connected subspace of X, then Y lies entirely within either C or D. Can you think about this question here? You have a set X, right? You have a set X, and you have some separation C and D. Okay, if Y is a connected subspace, so that means you cannot split it then this C here, right, should either lies in C or lie in D. Really lie within C or D. Makes sense or not? Does it make sense? First, make sense of this question and then try and prove it. Does it make sense? If this connected subset lies in between, what happens? You can split it up, right? Then you can take the intersection of C with so many C here. So let's name our connected C as maybe, it's named, so it's Y actually. Okay, so Y, right? So if it lies in between, right, what happens? You can take Y intersect C, Y intersect D to be your separation. Okay, so if it is a connected subspace, it must lie in either one. Okay, next. By the way, you can stop me if you have any question. So lemma, the union of a collection of connected subspaces of X that have a point in common, okay, meaning their intersection is 1 point. I mean, the intersection is 1 point, yeah, correct. So their intersection has 1 point in common, okay, at least 1 point in common. The point X in common is connected. Okay, everyone get the idea of this sentence here? So if I have a connected subspace of X, and then their intersection is non-empty, there's 1 point inside there, then the whole thing is connected. Okay, I want you to take close look on this proof, because this proof is really very animated. It's very animated. Please follow this proof. See how animated it is. Okay. So let's start with let A alpha to be a collection of connected subspace. Okay, so this is given by the question. We don't alter it. And then we name our point to be X. So let's X be a point in this intersection here. Okay, and we're gonna prove that. Y equals to Y equals to union of A alpha is connected. So we do the same strategy. Suppose it is not connected first. Okay, suppose it is not connected first. So suppose, on the contrary, that Y is split into C union D. Okay, is a separation. Y. What can we play around here? Try and follow this proof. This is very animated proof for connected. So what happened here? What happened to the point P? And what happened to the point P? P is the point in Y, right? So can it lie in both C and D or not? Cannot, right? Because C and D are disjoint already. So it must lie either on C or on D. Can only lie in one because there's no intersection between C and D. Did you guys imagine already? You have A alpha. Okay, there's 1 point in the intersection. Okay, suppose you can split the whole thing into 2 parts. So this P here must go to 1 C or 1 D. Like X. X must go to C or D. Okay, can you imagine? Okay, so keep this picture in your mind. Can go to C or can go to D. So suppose it is in one of them. Suppose P is in C. So P walk to C already. Okay. Then what can I do? Since A alpha is connected, just now what did we say? If you have a connected subspace, you must lie in wholly in C or in D. But P is in C already. And then A alpha intercept P is non-empty. So it must lie in C also. It cannot lie in D. Because if it lies in D, you will bring your P to D again. So if it lies in P, if A alpha lies in D, P is in A alpha, then P have to move to D. But I assume P is in C. So I need to pull A alpha to C also. So in this case, what? I can really pull every guy go to C. So meaning what? So that the union of A alpha is wholly living in C. This means what? This contradicts that. You want to say something? Yes, this means that D is empty. So contradict that D is not empty. Okay, correct or not? So this proof is very animated. You split your space into two parts first. Okay, then you talk about that common point. Now the common point, one thing, 1 to 2, you can only go one place only because they are disjoint. So you choose one place. Then you talk about A alpha. Where should A alpha go? Can go to D or not? If A alpha go to D, by the theorem before, every A alpha should lie there. But P is one point in A alpha. So you say P in D, P in C, contradiction. So my A alpha have to go to C also. So by the same reasoning, all the A alpha has the point in common with this X. So they all have to go to C. So everything go to C already. Then D is nothing. Okay, so proof is very animated. What is S and P? Because I might not put P, so I a bit confused with X and P. So we name it X, right? So just X. Yeah. Yeah. Okay. Yeah. P is the point. Because I a bit confused with it. Okay. Yeah. Does it make sense? So the point in common, link people together. Okay. So if you want to connect things together, yeah, this point in common is quite important. Okay or not? What time is it? 12:39. Okay. Let's continue. Keep go on. Let's keep going. So we can define a few things, okay, to describe our set better. So if let me see, did I left any theorems or not? Yeah. Okay. So we can say that if A is an element in X, a topological space. So maybe I put topological here. The largest connected set containing A is called the connected component. Okay, what does this mean? What does this mean? So you can look at A and then look at everything connected to it. And then you form a set. And then you form the largest one. Okay. Then this is called a connected component. Okay, connected component. Theorem here. So the theorems here is very easy to prove, is to say that the connected component of a topological space X form a partition of X. So in other words, this connectedness here, right, become a equivalence relation. Okay, if you are connected with me, then we stay in the equivalence relation, which we call the connected component. Okay, no? Okay, so this is very easy to prove. So for example, just now, we have this roses, right? Okay, we have this roses here. Okay, if I take away the cut point, okay, I take away all the cut point here. Okay, maybe make it black. Take away all the cut point here. Okay, how many connected component in the first one? How many connected component in the second one? 2 and 4. So you need to prove that, inside that, we call leaf, right? That leaf, they are connected to each other. How to prove it is connected? There is no separation. Okay. So a bit troublesome, but in future, future, because no time already. So in next week, we will introduce something called path connected. Okay, if you are connected in this Rn sense, you can use path connectedness. Okay, but not the other way around. Yes, partition of what? Partition of what? Partition of X, sorry. Sorry, my brain cannot work with my body one. My organ and my it's separate one. My hand-eye coordination not good. So please check if I miss something. Okay, let's continue a bit more, then we finish up. So yeah, so proof, you need to prove, for now you still need to use separation to see it, okay? And then next week we use path connectedness to see. Theorem, next theorem. I think we won't prove this, it's very easy exercise, but we will discuss about what it's trying to say. So let A be a connected subspace of X, okay? If A is a subset of B and B is a subset of A bar, then B is connected. So what kind of concept is this? You have a connected subspace, okay, and then you have a potentially bigger set that contains A. And then what's the other thing saying? B is in the A bar. What does this say? Every point in B is a point in A bar. What's a point in A bar? Either A or either limit point. Okay. Okay. Then you will get that actually B is connected. Okay. Yeah, this one is a very good exercise. You can try and work it out. Okay. Yeah. Okay. Final thing, we also don't prove it. This is called the about finite Cartesian product of connected space. So a finite Cartesian product of a connected space is still connected space. Not that I didn't mention whether this is under box topology or product topology. You know why? Because connectedness, you need separation, right? Separation, you need open set. So you need to tell me who are the open set. So to tell open set in product, Cartesian product of set, you need to tell me whether you use box or product. So why I didn't mention box or products here? Yes, this is a finite Cartesian product. You can prove that under finite Cartesian product, those two should define the same thing. Okay, one using basis, one is sub-basis, then you can build each other. Okay, so you see this theorem works for finite only. So meaning what? Infinite might not be true. Okay, so this is the case. Infinite might not be true. So why is it infinite might not be true? So let's take an example of the R omega again. What is R omega? You just Cartesian product your R denumerably time. Okay. Denumerably time. And what can you do here? So if I want to say that this is not connected, right? I need to build a separation. Okay, I need to build separation. So how to build separation here? So one way given by your book is you can take all bounded sequence and all unbounded sequence. Right? This two set is disjoint, first of all. Non-empty, quite obvious. You can build, right? What else? Sorry. Yes. How about openness? How about how to see openness here? See openness here. How to see openness here is the problem here. Can you write the set as a union of some open set? Open set in this okay, sorry, this is what under box topology. I forget to fix this. So who are the open set here? Right. We want to talk about open set here. Who are the open set? So under box topology means what? The open set, the basis here is what? Product of open set in R. Okay. Product of open set in R. Okay. So the claim here is given a point in R omega. So you can write A to be A1, A2, A3, dot, like that. Okay, how to form an open ball around it? Open neighborhood. So you can consider this open neighborhood to be something like, if I'm not wrong, just do like this, -1 + 1. And so on. Okay. And then if you do this ball, right, will avoid unbounded sequence. This ball will avoid unbounded sequence. So this open ball is lying completely inside this. Everything inside here will be all bounded sequence. You can show that. Okay. Because if you have an unbounded sequence, right, these terms also will form unbounded sequence. Yeah, you can try and show that. Okay. This ball here shouldn't contain. Okay, let's say this. Okay, what I mean is, if given this is bounded sequence, then this ball won't contain unbounded sequence. Okay, so that it lies completely inside one category. Similar the other way around. Okay, if you are a unbounded sequence, then you form this ball, then this ball won't contain bounded sequence. Makes sense? What is bounded sequence? Bounded above and bounded below. Yeah, try and show this. Okay, if you have problems seeing this again, we can discuss next time. Okay. Won't contain any. Okay, any question before we take a break? I mean, until adjourn until next week. Everyone clear about exam stuff? Not clear. Why are you not clear? You want to take exam or not? For free? You don't need to prepare also. Yeah. No pressure on you, man. Pressure on me, right? Okay. So I will make announcement again for exam.